So today we will be discussing about the closure property of CFL. So before discussing about the closure property of CFL, let us know what is CFL. So CFL is basically a context-free language. It is basically a language that is generated by a type 2 grammar, that is context-free grammar, and accepted by push-down automata. So first let us know what the closure properties are, or how we can say that a context-free language is closed under some specific operation. We can say that a context-free language is closed under some specific operation if after applying that operation on the context-free language we are getting a language that is also context-free. So now let us talk about some properties under which, or some operations under which the context-free languages are closed. So the first operation under which the context-free language is closed is your union. So let us talk about how it is closed under union. So let us take two languages, L1 and L2, be two languages that are accepted by, let L1 and L2 be two languages accepted by context-free grammars G1 equal to V1 P1 sigma P1 S1, and L2 be accepted by context-free grammar V2 sigma P2 S2. So basically L1 union L2 will be accepted by a context-free grammar G, that is V sigma PS, where V is V1 union V2 union S, and P is basically the production rule, union P2 union S goes to S1 or S2. Is it? So we can see that L1 union L2 is also being accepted by a context-free grammar. Hence we can see that it is closed under union. For an example, let us say L1, that is A raised to the power n, B raised to the power n, C raised to the power m, where n is greater than 0 and m is also greater than or equal to 0. This is a context-free language, as we know that for n A's that are pushed into the stack, n B's are popped out, so it is a push. It is a context-free language. And L2, where A raised to the power n, B raised to the power m, C raised to the power m, where n is greater than or equal to 0 and m is also greater than or equal to 0, is also a context-free language. As for n number of B's that we push into the stack, we can pop m number of C's, so hence it is also a CFL. So their union, that is L1 union L2, which is A raised to the power n, B raised to the power n, C raised to the power m, union A raised to the power n, B raised to the power m, C raised to the power n, m is greater than or equal to 0, is also a context-free language. Hence we can say that context-free language is closed under union. The second operation that it is closed is concatenation. So similarly for concatenation, we can say if L1 and L2 are two languages accepted by context-free grammars, G1 equal to V1 sigma PS1 and G2 is V2 sigma PS2 S2, then L1 dot L2 will be accepted by a context-free grammar. That is G equal to V sigma PS, where V is V1 union V2 union S and P is P1 union P2 union so on S2. So we can say that it is also closed under concatenation. Now let's see an example. Example would be L is a raised to the power n b raised to the power n greater than or equal to 0. We all know that it is closed, that it is a context free language. L2 is c raised to the power m d raised to the power m this one is also a context free language. So their concatenation, that is L1 dot L2 is a raised to the power n b raised to the power n c raised to the power m d raised to the power m, where n is greater than or equal to 0 as well as m is greater than, is also a context free language. This is also a context free language. As you can see, for n number of a's that we push, we can pop n number of b's, and for m number of c's that we push, we can pop m number of d's. So it is accepted by push down automata, hence a context free language. So we can say that context free languages are closed under concatenation. Third operation under which it is closed is clean closure, also denoted by star. So we can say if L1 is accepted by context free grammar, G1 equal to sigma P1 S1, then L1 star will also be accepted by a context free grammar. G equal to V sigma PS, where V is V1 union S and P is P1 union S is going to S1 epsilon. So we can see that for clean closure it is also accepted by a context free grammar, hence we can say that it is closed under, that context free languages are closed under clean closure. So now let us talk about the operations under which context free languages are not closed. So the first operation under which it is not closed is intersection. So context free languages are not closed under intersection. We can see that by an example. Let L1 is a raised to the power n, b raised to the power n, c raised to the power m, where nm is greater than n greater than equal to 0 and m is also greater than equal to 0. L2 is a raised to the power n, b raised to the power m, c raised to the power n is greater than equal to 0, m is greater than equal to 0. Its intersection will be a raised to the power n, b raised to the power n, c raised to the power n is greater than equal to 0, which is a very popular example of not being a context free language. We all know that it is not a context free language, since three non-terminal symbols are dependent on same n. So basically for n number of a's we can pop b n number of b's, but c's will remain as it is. So we can say that it is not accepted by positional automata, hence not a context free language. So this clearly shows that context free languages are not closed under intersection. Second property under which it is not closed is complementation. So to prove this, let us first consider that CFL is closed under complementation. So L1, if L1 is context free language, L2, L1 complement will always also be a context free language. If L2 is context free, L2 complement should also be context free, and so their union should also be context free, and its complement should also be context free, which is L1 intersection L2 by De Morgan's law. Now we know that it is not closed under intersection, hence we can say that we contradict the fact that CFL is closed under complementation. Hence we can say that CFL is also not closed under complementation. Okay, so that is it. Thank you.